Okay, so for the last bit of work for this week, I'm basically asking you all to do the same thing that we did yesterday for this green mystery mass for the blue and red one, so experimentally determining those two different masses. Luckily today you don't have to get this spring constant for that zero notch spring again, so you can already use your value that you found yesterday and determine those two masses the same way that you did in yesterday's Thursday work. Now, once you have that, the last question that I ask you all to solve and to think about is if we could combine this blue mystery mass with the red mystery mass, if we could just sort of put those both in a bucket and hang that on the end of this spring, how far down would this spring stretch, or what would that displacement be from these two masses being sort of put together? And there are a couple different ways that you could think about that. I'll offer one possibility here where let's say, just for example, that I got the mass of, and I'm going to use some subscripts here. Let's say I got that the mass of the blue object was, let's say that we got that it was 0.4 kilograms. And let's say that we got that the mass of our red object was 0.1 kilograms. Now, the way that it occurred to me to do this problem is if I want to know the mass of this new purple object, that is the combination of these two, I'm just going to add those two up. So maybe I got 0.5 kilograms for the total there if I combined our red and blue masses. And then I still know what that, if I drew a free body diagram, because I can't go through one of these videos without drawing a free body diagram, I still know that we've got our gravity and a spring force, and since those are the only two forces acting on this object, which we know from this, like running this simulation for a week now, we know that eventually that object will come to rest, which means that these two forces need to balance each other out. That's why this object can be stably at rest or stably at equilibrium. So we can use our mass to calculate that force of gravity, which is equal to our spring force. We can also use whatever spring constant we have from before. So I think in the last video I used 5 newtons per meter as our example. And so whatever we get for this mass, let's say I had this 0.5. So if I plugged in, and I'm skipping a step sort of right now, what I'm doing is I'm plugging in this 0.5 kilogram mass into our m to get that force of gravity. So I think 0.5 times 9.8 should be 4.9 newtons. And so that is equal to our gravity force, but also that is equal in magnitude to our spring force. So we can use Hooke's law. And I'll start writing this in. Hooke's law, spring force is equal to negative kx. And then let's plug in our 4.9 equal to negative 5 newtons per meter times x. And so then at this point we would divide both sides by this negative 5, because that's what's next to our variable that we're trying to solve for. That's right now being multiplied by the variable that we're trying to solve for, so we have to do the opposite of multiplication to cancel that out. I'm not going to show that, I'm not going to write that out here, but if we did do that division step, so 4.9 divided by that negative 5, we would end up with an x equals negative 0.98 meters. And the reason that that negative is there is because this would be a downwards displacement, just like all of the other masses were when we hung them from these different springs. That displacement is going downward, so our displacement could in fact be negative here. I usually write these as positive because that downwards negative displacement is sort of implied in a vertical hanging spring and mass system, but you could very well include that in your answer.